To motivate our discussion of normalization, in other words, why do we do normalization, we pointed out that if we take all the information that we want and stick it in one table, and very likely that table will end up having multiple themes, and as soon as you have multiple themes in one table, now you end up with redundancies, which ultimately result in update, insert, and delete anomalies, and pretty soon your database becomes inconsistent, and that's bad news. So having multiple themes in one table, which happens when you put all your information in one table, is undesirable. And we said that the solution to this is to start taking this one table and gradually, progressively split it up into a collection of smaller tables where each table addresses one theme. And we showed you one example of that. So the advisor and student, the one table that contained the information on advisor, rather the student and the resident advisor for the dorm, we just split it up into two tables. I didn't tell you how, but this is the end product of normalization. So now we will continue on this journey of normalization, and we will discuss in this tutorial a very, very basic fundamental concept that underlies normalization, and that is the concept of functional dependencies. So functional dependencies lie at the heart of normalization. That is the process by which you take a table and cut it up into smaller tables. Okay, so what we have done so far is just we informally used words like themes, multiple themes, and so forth. Obviously, when you have large tables, you can't eyeball the thing and do it informally. There has to be a rigorous process for cutting up the table, and the conceptual foundation for that is the concept of functional dependencies. So this tutorial is devoted to functional dependencies. So let's see what that is. To give you, first of all, it's written in the following manner: X, right arrow, Y. So this is the manner in which it is written, and the way you read it is from left to right. You say X determines Y. X functionally determins Y. Okay, either this, or you can say it in reverse, that is Y is functionally dependent on X. And pretty much, people drop the word functionally and we just say X determines Y and Y depends on X. Okay, but that's the symbol that's used, the right pointing arrow. So there is a left side and there is a right side to a functional dependency. The left side is called the determinant and the right side is called the dependent. Okay, so those just in terms of terminology. To give you a simple example, so if I know the radius of a circle, I know its area. Okay, so if I give you one value for radius, you can give me exactly one value for area. Okay, so that's the concept of functional dependency. Now, if you take it to in the context of databases, we will adopt the following definition: that if X determines Y, if X functionally determines Y, then for each value of X, there is at most one value of Y. Okay, or X uniquely identifies Y. Why at most one Y value? There are situations where if I know the value of X, I may not know the value of Y. Okay, but if I do know the value of Y, it's exactly one value. Now remember that both X and Y can consist of multiple attributes. So we say X determines Y. So but X and Y themselves could be either single attributes or multiple attributes. And also, this is extremely important, this functional dependency, X determines Y, these are relationships between attributes in the same table. This is absolutely critical. So both X and Y must be from the same table, and we are simply trying to figure out relationships among attributes in one table. Okay, because after all, these will be used to split up the table into smaller fragments. So we're trying to study the relationship between attributes in the same table. All right, so let's look at some specific examples here. So let's take the first one. So your X is G number and your Y a student name. If I give you a value of G number, if I give you one value of G number, you can give me exactly one value of student name. It uniquely determines student name. Okay. Notice that the reverse is not true. This is not true. That is, student name does not determine G number, because if I give you a student name, let's say I say Dan Brown, that's the name of the student, you cannot give me a unique G number, because we know from the realities of life that there could be two Dan Browns. Okay, two different people having the same name is not uncommon at all. So knowing X, knowing student name, doesn't give me a unique G number. But if I know the G number, then I know the student name uniquely. Okay, so let's look at two more. If I know the student name, does that functionally determine student email? So this is X and this is Y. Okay, knowing the student's name does not functionally determine the student email, because a student could have multiple emails. Okay, so knowing the student's name does not give me a unique value for student email. Furthermore, you could have multiple students with the same name, and they would all have different email addresses. So clearly this thing is not true. This relationship, this is not a correct functional dependency, this one. However, if you look at the second example, if I know the student's email address, okay, so if I know this value of X, that uniquely determines one value of Y. So one email address, one student email address corresponds to exactly one student name. So I hope you get the idea that the direction is very important. If X functionally determines Y, that does not necessarily mean that Y functionally determines X. The reverse need not be true. Okay, so let's look at a last example over here. Now, if I know the G number of a student, do I know the student email uniquely? If this is X, do I know Y uniquely? And I would argue, no, I don't. Okay, it depends what you mean by student email. If by student email you mean the Mason email address, then we know that each student has exactly one Mason email ID. So then I would say, if I give you one value of G number, you would be able to give me exactly one value of the student's email, since it's the Mason email address. However, if by student email I mean any email address that the student uses, then this functional relationship would not be true. Then this would not be a correct functional relationship, because if I give you a G number, that might correspond to the student's GMU email address, to their Hotmail email address, whatever. There could be multiple email addresses. Okay. On the other hand, you look at this last example over here. If I give you the student's email address, I give you one email address that belongs to the student, then you can immediately give me a unique value of G number, because one email address cannot belong to more than one student. Okay, so this would be a correct functional dependency. So all these examples that we have gone through is an attempt to show you what functional dependencies mean, how they are written, and the fact that it's directional. So when we say X functionally determines Y, the reverse need not be true. Okay, sometimes it is. For example, if we say SSN and driver's license number, we know that each person, at least in the US, has one social security number and one driver's license number. So if I give you the value of a social security number, you can give me exactly one value of driver's license. Similarly, if I give you one value of driver's license, you can give me exactly one value of social security number. So this is an example where X functionally determines Y, and also the reverse is true. Y functionally determines X, but usually this is not the case. So functional dependencies are directional. Always remember that if X functionally determines Y, then the reverse is not necessarily true. Okay, so now for some definitions. So from your study of the relational data model, you know what a primary key means, you know what a candidate key means. Okay, and right now, since we have introduced the concept of functional dependency, which is written like this, I also defined for you that the left side of a functional dependency is called the determinant, and the right side is called the dependent. Okay, so now that we have all our definitions in order, so you can see that a primary key of a relation will functionally determine all other attributes in the row. Why? Because we know from our relational data model that a primary key uniquely identifies a row, every row in a table. What does it mean to uniquely identify a row? So if you think of a relation, it has lots of columns, and let's focus on one particular row. And let's say this attribute is the primary key. What does it mean for this attribute to be the primary key? The definition is, if I give you the value of the primary key, you can tell me all the other values in that row. Okay? So the primary key uniquely identifies the full row. So in the language of functional dependencies, it means that if I give you this value of x, the primary key, then you can tell me all these other values in that one row. Hence, we can say that the primary key functionally determines all other attributes in that row. So now by reverse logic, we can say that if, when we are doing functional dependencies, if we find a particular attribute that uniquely identifies all other attributes in the table, then that attribute could serve as a key for the table. Okay, so there is some correspondence between keys and functional dependencies. So all that we need to remember for now is that a primary key uniquely identifies every row in the table, and hence it functionally determines all other attributes in that row. So let's apply these concepts now to an example. So what kind of dependencies can we identify over here? Okay, so before we do that, you can see this in this one table, there are multiple concepts that seem to be present in this table. So if I look on the left side, two columns, these two columns contain information about projects. So one concept or one theme that's floating around in this table, one theme that's present in this table is projects, so properties of projects. And if I look at the second piece over here, these few attributes, so we have the employee number, the name of the employee, the job classification of the employee, and the hourly rate that the employee charges, then that seems to be information about employees. So we have a second theme related to employees, and we have a third theme here, hours worked, which really doesn't belong to either the employee or the project, but it sort of belongs to both, in the sense that it tells you how many hours an employee has worked on a particular project. So if I look at 23.8, that first value, what that means is employee June Arbo has worked for 23.8 hours on project 15. Okay, so there is a third theme that's floating around in this table, and that has to do with hours worked in a particular table. And we know by now that if there are multiple themes in a table, then there will be anomalies, there will be update, insert and delete anomalies. But so we know we will have to normalize this table. Now the foundation for doing that normalizing is functional dependencies. So let's see informally what kind of functional dependencies there might be present in this table before we actually show it formally. So if I just look at the contents of this table, you can see that if I know the project number, I know the project name. Okay, so if I give you a value of project number, you can give me a value for project name. So it seems to me that project number determines project name. That's a functional dependency that seems to be present in this table. All right. Now, if I look on the next few columns, let's look at employee number and employee name. So let's try and find an employee that's present at least in two rows. So here is employee 106 and here is employee 106, and you can see that it corresponds to William Smithfield. So just by looking at this table, it seems to me that if I know employee number, then I know the employee name. So this is X and this is Y. The reverse may not be true. You may have two employees with the same name but different employee numbers. So that's a second functional dependency that seems to be present in the table. Okay. Furthermore, if I know the employee number, I also seem to know the job class. I can tell you what the job class is, because if you tell me employee 101, then I'll tell you that that employee is a database designer. If you tell me employee 105, 104, then I will tell you that that employee is a database designer as well. So if I know the employee number, I also know the job class of the employee. All right. Now, if I go a little bit further to the right, there's an interesting functional dependency over here. So, and this is just an observation on my part of the contents of the table. It seems wherever I see database designer, I see 105 as the hourly rate. Okay. Here, let's see, here's again database designer. Here's another database designer. So wherever I see database designer as the job class, I see 105 as the hourly charge. That suggests to me that job class determines hourly rate. So the hourly rate depends on the job class. Okay. So these are some ways in which I'm trying to tease out by looking at the data what kind of functional dependencies there might be in the table. But just be aware that looking at the data alone is not enough to identify functional dependencies. You must have a good knowledge of the domain. So in this case, you must have a good knowledge of how the business runs projects. Okay, does it only allow one employee to work on one project, or can one employee work on multiple projects? So depending on the business rules, depending on the rules of the domain that is represented in this table, the functional dependencies might turn out to be different. So this is a word of caution. This is a very important point, that yes, you look at the contents of the table when figuring out functional dependencies, but the most important piece of information that you need is to have domain knowledge, specifics about how things operate in the environment of that particular table. That's the major way in which you try to identify functional dependencies. So now, using that logic and that reasoning, the functional dependencies that we came up with for this table are the following four. So if I know the project number, I know the project name. This is one functional dependency. If I know the employee number, this is X, then I know the employee name, the job class, and the hourly rate. Okay, so I know all those three things as soon as I know employee number. If you give me one value of employee number, I can give you exactly one value of employee name, one value of job class, and one value of hourly rate. Similarly, when I showed you in the previous slide that job class seems to be determining the hourly rate, and I made that argument based on my observation about database designer, and it also seems to be true for other job classes. So wherever I see programmer, I see $35.75. So that's even strengthens my belief that job class determines hourly charge. So if you give me one value of job class, I can give you exactly one value of the hourly rate. Now the last piece is hours worked, and in order to determine hours worked, I need to know both the employee number and the project number. So do you see now that for this functional dependency, the left hand side, the determinant, is composite. So X consists of these two attributes, employee number plus project number, determines hours. So for the first three functional dependencies, the determinant was one attribute, project number or employee number and job class. So for three of those functional dependencies, the determinant was a single attribute. But for the last functional dependency, this one, the determinant, in other words, the left side of the functional dependency, this is composite. Okay. So these are the functional dependencies that exist in this particular table, and in the next tutorials you will see how these functional dependencies are used to cut up this table into smaller tables so that each one ends up holding one theme, and by doing that you get rid of the anomalies, the update, insert and delete anomalies.